day again. I am here, Salle, the moderator of the Liceo Math Club, and today we're going to talk about proof by contradiction, and this serves as the part 2 of our previous one, square root of 2 is irrational. Okay, so this proof by contradiction is one and popular as a technical proving, which is indirectly. So in Latin, this is popularly known as soliloquio ad absurdum. We have here number 1 and number 2. This will serve as your exercise if you know to answer this. So I'm going to read this. There is no smallest integer. And number 2, there is no greatest even number. So you may pause the video if you want to have a glimpse or to answer this. Okay. So for number 1, I hope you got an answer there or start with an answer. Okay. So for number 1, there is no smallest integer. So notice we cannot prove this directly. Okay, so for example, if I'm going to write 1 as the smallest integer, there will always be a 0 which is smaller than 1. As you can see, of course, 0 is smaller than 1. So when you say 0 is the smallest integer, negative 1 is even smaller than 0. And negative 2 is smaller than negative 1. So if we're going to have a bet, say try this kind of bet, I'll say 9999999, and this is negative 99. So I could always say that, well, there is lesser than this, which is negative 9999999. Just put another 9 from the 7 9s to 8 9s. And you could always put a negative 999 and so on until you run out of 9s. So from this, you cannot prove this directly, that you can say that there is no smallest integer. So the proof which is direct is kind of absurd. So we're going to use the proof by contradiction. Again, what is proof by contradiction? That is, we will make an argument and assume that this is false, meaning there exists a smallest integer. And from that false statement, we will try to falsify that one. And if we falsify the false statement, we are saying indirectly that this is a true statement. So let's start from here. So how can we start the proof? So proof. We will let, say, a random variable, say alpha. Let alpha be the smallest number, the smallest integer, say. Okay. So we have an alpha here, which is the smallest integer, and we will try to disprove that alpha cannot be the smallest integer. Okay, since imagine alpha to be a very small number. Okay, in fact, it's the smallest. So how can we make an argument, okay, to disprove that alpha is the smallest? So very simple yet powerful argument can be done. Okay, we can say, but imagine alpha. We're going to minus 1 from that alpha. Okay, so imagine alpha as the smallest integer, but then if we're going to minus or subtract 1 from alpha, this clearly states that is alpha minus 1 is clearly less than alpha. So, meaning, this new entity is the smallest integer, not this one. I hope that is clear for everyone about that argument. So therefore, we have told that this is not the smallest integer because this one is the new entity, which is the smallest. Okay? That is, we have disproved it. So this is a contradiction. Okay. This is a contradiction of our statement here that alpha is the smallest because we have known that alpha minus 1 is smaller than the smallest integer. So that's a contradiction. Thus, we can say that there exists no smallest integer. Okay. Okay, so from that number 1, we're going to answer this number 2 using the same firepower from number 1. So a very simple reductant absurdum would be that. There is no greatest even number. Again, we cannot prove this directly. If we do, say we have 1 million, okay, 1 billion, that's even, and that's a big number. But this is less than 1 million and 2. Okay? Did I get over 1? That's 1 million and 2. And this is even less than 1 million and 4. 1 million and 4. So we cannot prove this directly again. Even if we have a series of numbers, 9, 9, 9, 9, 9, 9, 9, 9, 8. So we can disprove this by having another even number. Okay? So we are going to create an argument that really proves that there is no biggest even number. So what is the proof here? So again, using the proof by contradiction, we will assume that there exists some number, an even number, which is the greatest. So we will let, enough with the alpha, let's have a beta. Let beta be the greatest even number. When I say even number, that will be automatically an integer, an even integer. Okay? So we have assumed that beta is the greatest even number. So what we're going to do, this is our argument. We will try to disprove that beta is not the greatest even number. In that we're saying that there exists no greatest even number at all. So, but the same way with number 1 actually. Imagine beta plus 2. Okay, so beta is the greatest, but then if we're going to add 2 from the greatest number, greatest even number, this is still an even number. So that is beta plus 2 is greater than beta. So this new entity is the greatest even number, but from our argument, we're saying that beta is the greatest. Therefore, this is a contradiction. A contradiction from our previous statement. Contradiction. From our previous statement here, that it's the greatest. Because we have disproved that if we're going to add 2 from this greatest, it will not be the greatest. Thus, by proof by contradiction, there exists no greatest even. That's the okay, so we're done with the 2 examples here. Let's have a popular theorem to be answered by you guys, the viewers. So assignment, prove the statement here using the proof by contradiction. That's written at Theorem. The theorem here is very popular. It's Euclid's theorem, which states that there exist infinitely many primes. So there are infinitely many primes. Okay? Just take note that prime numbers are integers that have only a pair of factors, which is 1 itself. Okay? That is, P is a prime if and only if P is equal to its number itself times 1. Okay? So that's it. Thank you for watching. Kindly to subscribe to our video channel to get the latest notifications, and see you soon. Bye.